for students, some school travel grants for conferences and whatever. And what is very important is for next year, we reduced the membership fee of about 60% for regular members and 90% for students. So if you students are not a part of DEIS, you can join the DEIS community for just $1 US. So it's very, very cheap and affordable for everyone around the world. Okay, so after this very brief presentation of DEIS, let's go into the focus of my talk, which is HVDC. In particular, HVDC links are nowadays it's one of the hot topics of now and the future. The reason why is that the electric network is expanding a lot due to the increasing growth of renewable energy sources inside the power network. And in order to create a stable connection between high power networks, of course, HVDC is much better than HVAC because it provides a higher reliability and in particular also high resilience. And it's very efficient also for long distance transmission. For instance, the continental grids nowadays are made by HVDC connections, which is becoming the backbone of the electric power transmission system of the future. I give you just an idea. One of the major cable company, which is located in Italy, one of the major in the world, they told me that the 90% of the new cable installation, I mean new very high voltage cable installation, are HVDC. Let's say around the world, HVDC connections are exponentially growing. And the reason for that is that with HVDC, you can integrate very well the renewables inside the power networks. For instance, here I've reported 3 examples of what Europe is willing to do in the next years, let's say. We have a lot of renewables in the north of Europe, like wave energy, hydro energy, or wind energy. And we have a lot of solar energy that can be provided in the south of Europe. So the idea is to create some DC highways from north to south and from east to west to interconnect Europe and put together all the renewable energy sources that can be created. And in particular, nowadays in Germany, there are 4 very long HVDC connections called the German corridors. One is here, second, the third, and the fourth, to connect the north of Germany with the south of Germany. North of Germany is very rich of renewables, while the south of Germany is the richest part of Germany, where there are the major loads, electrical loads of the country. So it's very important to feed these loads with renewables that come from the north. And the idea of the future is to create a sort of super grid, no? A European North Africa super grid to put together all the renewable sources that can be created in each part of this continent. So all the links, these are very long links, are thought of using HVDC systems. Which kind of insulation system we can use for HVDC transmission? For sure, if we want to create overhead lines, in that case, of course, the electrical insulation is the insulation that you can find in the overhead insulators. But overhead lines that are good for very long distances, sometimes they are not seen very well by local communities because, of course, they are ugly. The local community, they don't want to see overhead lines, and so it's very difficult to build new overhead lines, in particular in Italy, but also in Europe. I don't know, in India, perhaps you can have some, let's say, desert areas. In that case, it's not a problem. But if you are in a very densely populated area, it's very difficult to create overhead lines. So the possibility is to use insulated cables. These are, of course, let's say compulsory if you are creating a submarine connection, because for length longer than 50 kilometers, HVDC is the only technology that is available. You cannot use AC due to the reactive power that is necessary to feed the cable. But sometimes also you can see replacement of overhead lines with underground cables, because, as I told you, they have a low environmental impact, so they are more accepted by local population. And in that case, we have three main technologies that can be used for HVDC and also extra high voltage cables: the so-called mass impregnated system, oil-filled materials, and the fully extruded cable, which use a solid, completely solid insulation, while the other two, the mass impregnated and the oil-filled materials, they have a mixed solid liquid insulation. And the fully extruded cables are now the frontier of the HVDC insulation systems, because they are, let's say, cheaper and also more environmental friendly, because of course they don't use mineral oil that can be of some concern in case the cable is damaged, for instance, and it can contaminate some area, of course. But the problem is that fully extruded cables, which means polymeric extruded with polymeric extruded insulation, even if they are very common for AC application, they were used for AC application since 1960, I would say, 1970. But for HVDC, up to, let's say, a few years ago, they were not the benchmark insulation system. Okay, so they were the reason for that, the fact that were not so common for HVDC, is that polymeric insulation had some reliability problems if fed by DC. In particular, these problems came when we had voltage polarity reversal. And this can occur under HVDC if you want to reverse the power. Sometimes you have polarity reversal, and this can create insulation failures. But nowadays we have extruded polymeric HVDC cables that are qualified up to 525 kilovolt. So we have developed electrical insulation that is reliable also at high voltages. But the problem is that now we want to exceed 600 kilovolt. So the reliability concern about the fact that polymeric insulation can have, of course, is still present. In particular, in joints for deep water application, still the use of polymeric fully extruded insulation is not so common due to some reliability problems. And then the reliability problems that this kind of insulation have are related or associated with space charge accumulation. In the 90s, at the end of the 90s, someone wanted to use the XLPE material that was used for AC applications for DC application. And the problem was that what happened is that the cable, the AC cable fed under DC, even at low electric field, let's say not very high electric field, let's say 10 kilovolt per millimeter, the problem was that after a few tens of hours of service, as you can see here, 60 hours, the cable failed. And the reason for that is that the electric field at the cathode and at the anode, so at the electrodes of the cable, increased a lot during the polarization, the application of the voltage. And the reason for that is that under AC, the electrical insulation is not so critical. The electrical insulation used, the XLP used for AC had a lot of cross-linking byproducts. And these cross-linking byproducts, if you apply electric field, then they create the ionic species that can migrate to the opposite electrodes, creating space charge accumulation. So the idea was to use an AC insulation for DC. You have to remove all the cross-linking byproducts and volatile products. In that case, you can reduce space charge accumulation. You can reduce the increase of the electric field, and you can improve the reliability of the cable. So this was, let's say, the idea that pushed the cable company, at the end of the 90s to use polymeric insulation for HVDC. But remember that the electric field was still quite low. The design electric field was below 10 kilovolt per millimeter. The problem regarding space charge accumulation is that when you apply a DC field at a solid electrical insulation, what you can have is a lot of, let's say, activities inside the insulation. In particular, you can have injection of charge from both the cathode and the anode. So you can have injection of negative charge or positive charge from cathode and anode respectively, or you can have dissociation of electric species inside the material, like I told you before, the cross-linking byproducts, the volatiles, that were inside the material, they could dissociate and create ionic charges that can then move inside the material. And this charge, if this charge cannot be transferred very rapidly along the insulating material, then can stay for a given time in some energy state of the polymer, in particular in the amorphous region, which are called traps. And this charge, net charge that is trapped in a given region of the space is called the space charge. This space charge becomes quite important at high fields because the injection of charge at the electrodes, the charge that we have seen here, the negative charge coming from the cathode, the positive charge coming from the anode, this charge increases these injections with the field and the temperature also. So increasing field and temperature, you can have a lot of charge that is injected in your material. We have then another mechanism, which is the charge transport inside the material bulk. And this charge transport occurs from one trap to another trap. This negative charge from here to go to another trap can hop or can tunnel from one trap to another. But this takes time, of course, and depends a lot on the trap depth. So the deeper the trap, the slower is the transfer of one charge from one trap to another one. And so if the charge remains for a longer time in a trap, then inside the insulating material, then of course can distort the electric field. We have also the extraction of charge. When the charge has reached the opposite electrode, then it can be extracted from the material, but this takes time, of course, also. It is called delayed extraction. And also this charge extraction is field and temperature dependent. So the local electric field is not, let's say, uniform. Our electric field is not the one that we are thinking when we, for instance, divide the voltage time for the thickness of the material. If we are in a plane geometry, if we are in a plane geometry, we know that the electric field is uniform, and it's given by the ratio between the voltage applied and the thickness of the material. But this is not this is the average field. This is not the case when we have some local charge that are present inside the material. In that case, the local field, the applied field, can be affected by the space charge that is present. And the situation is more complicated because we need to take into account the local charge density. And we can have a field that is increased or decreased depending on the kind of charge that we can have. In particular, we can have homocharge or heterocharge. Homocharge is the charge, you can see here a space charge pattern where this is the thickness of the material and this is the time of the voltage that is applied. So you can see that this is negative charge, this is positive, okay? So we see that we have accumulation here of negative charge close to the negative electrode. This is a homocharge. As here, we can see positive charge accumulating close to the positive electrode. This is homocharge. The homocharge can reduce the electric field with respect to the average field at the electrodes here and here, while it can increase a little bit the electric field in the middle of the material, okay? Because of course, remember that the integral of the field is the applied voltage. So the applied voltage is still the same, but the local field can change due to the space charge accumulation. While we can also have heterocharge accumulation. You can see here this positive charge accumulation close to the negative electrode. This is heterocharge accumulation. And heterocharge accumulation is very dangerous because it can provide an increase of the electric field close to the electrode with respect to the average field. And of course, if you have an increase here, you will get a decrease of the field in the middle of the electrode, in the middle of the material. But the problem is that this increase at the electrode interface, or the interface between electrode and the insulating material, is very dangerous because it can, increasing the field, it can provide more injection of charge inside the material because the injection of charge is field dependent. So if you increase the field due to heterocharge, then you can inject more charge in the material. And this can create a further distortion of the electric field. So it could be a process that can provide very quickly cable insulation failure. Okay, so heterocharge is very, very dangerous. While homocharge, it's not so dangerous. We will see a case where also homocharge can be a little bit dangerous. And this is another example. No? You see here a 3D pattern where you see a packet of positive charge that during time moves and reaches the negative electrode, creating heterocharge. And as you can see here, the electric field close to the negative electrode becomes higher and higher, okay? And can be also, let's say, in that case, is about 90% higher than the average field, that is this one. Okay, this is the average field, and this is the localized field close to the negative electrode, which is very, very high, as you can see here. So, what is, let's say, creating homocharge and heterocharge? There are some features of the electrical insulation that can create homocharge and heterocharge. This is a sort of balance between the injected charge carrier transport and how much charge is trapped inside the traps. This is determining the polarity of charge trapping. So homocharge versus heterocharge. Let me show you an example. This is a simulation that we did with, let's say, with simulating an injection following the Schottky law, one single trap level, and a delayed extraction of the opposite electrodes. What you can see here is that if we have a very weak trapping, which means very shallow traps, okay, not very deep traps inside the material, the charge that is injected from the negative electrode can reach quite quickly the positive one, creating heterocharge. And I told you that this is very dangerous, no? When you have heterocharge. But if you increase the trap depth inside the material of a factor of 10, you see that the homocharge, there is here a more extended region of homocharge that does not reach the counter electrode very easily because the traps are much deeper now. And if you increase also further the trap depth of another factor of 10, what you can see here is that you have only a very thin layer of homocharge close to the negative electrode. So you don't have heterocharge anymore. So playing on the trap depth, you can modify the trapping mechanism inside your insulating material. Or what you can do is that you can modify also the extraction rate. For instance, if you increase the extraction rate of a factor of 5 or 10, what you can see is that the heterocharge accumulation is reduced significantly. So you can play both on injection, extraction, and on trap depth, okay? In that way, you can change your space charge accumulation features of your insulating material. As I told you, heterocharge is very dangerous, no? Because it distorts the electric field. Homocharge, is it homocharge dangerous? Let's say it could be, but it could be under specific cases. Let me show here what happens in case of polarity inversion. So if you accumulate homocharge, what you can get is that the electric field before polarity inversion, as you can see here there is homocharge accumulation, is lower than what happens in the middle, okay? And this could be the applied field, okay, the average field, and you can see that the field here is lower. Then you apply a polarity reversal, which is, of course, requested sometimes to invert the power flow in your cable. If you apply the polarity reversal, the problem is that what is homocharge becomes heterocharge once you have reversed the polarity of your electrons. And what you can see here is that after polarity reversal, the electric field in correspondence of this electrode becomes very high. And this can create, of course, an extra stress to your insulating material. And this is very, let's say, can be very much, it's more evident when you do endurance test, life test on your material. For instance, if you do not provide any polarity reversal, you will see that at a given field, let's say this one, 150 kilowatt per millimeter, you have a lifetime that is about 300 hours, okay? But if you have homocharge accumulation and you do polarity reversal every 1 hour, what happens is that at the same electric field, you have a huge reduction of life. You see, from 200 to 20 hours. So 1/10 of reduction, 1 order of magnitude of reduction of reliability, due to the fact that if you have polarity reversal, also homocharge can create problems, okay? So homocharge can be tolerated if you do not have polarity reversal in your cable, but if you have polarity reversal on your cable, please, you must have really a negligible amount of charge that is accumulated in the cable itself, okay? So also homocharge cannot be tolerated. So how can we reduce the charge? If you remember, at the beginning, I told you that many years ago, the design field of HVDC cable was lower than 10 kilovolt per millimeter, because 10 kilovolt per millimeter was the threshold for space charge accumulation, okay? For XLP, for instance, you can see that this threshold is about 111 or 12 kV per millimeter. So below that value, we do not expect to have space charge accumulation. The problem is that we want to increase the service field because we are increasing the voltage of our electrical applications. So the field is now larger than 20 kilovolt per millimeter. But as you can see here, if you increase the field, you will increase the space charge that is accumulated in your material. So how can we do? How can we reduce the space charge, increasing the electric field? There are many techniques. One is mitigating space charge by using nanofillers. You know that nanomaterials can be used to modify the electric properties of insulating materials, creating new hybrid material, multifunctional, that can modify, you can in this way modify the electrical properties of your electrical insulation. There are many kinds of nanofillers that can be used. For instance, we can have spherical particles, whiskers, platelet, and you can see here a large group of fillers that can be used: silicon oxide, metal oxide, and for instance, the magnesium oxide is very much used to reduce space charge accumulation, nanoclays, or also carbon nanotube, graphene, and whatever. I show you a few examples of these materials that can be, of these nano materials that can be used to reduce space charge. For instance, we can add nanofillers to the base polymeric insulation and try to reduce space charge injection or increase the mobility of charge in the insulation bulk. Because if you remember, in this way, we can avoid to have heterocharge accumulation. The example that you can see here, that is used for some Japanese cable for HVDC, is using magnesium oxide. And as you can see, inside nanofiller of magnesium oxide, inside to be put inside the insulating material. As you can see here, without magnesium oxide, increasing the electric field, you can see a lot of heterocharge accumulation during time. While with 0.2%, you see that this heterocharge accumulation is reduced by increasing the field, and with 1% of magnesium oxide, you see that is completely suppressed, also at very high field. So this is one way of suppressing charge injection by creating deep traps. And these deep traps create a sort of barrier for space charge to be injected inside the material. But the problem is that the distribution and the dispersion of the nanoparticles is a key factor if we want to get very good property improvements. And it's not easy, also in lab scale applications. So you can imagine how it is difficult to guarantee this good dispersion for a cable insulation that is many kilometers long, okay? So another way is to apply these nanofillers on the coating of the cable, no? On the outer part of the insulation. There are many ways, introducing, for instance, deep traps on the coating, so not in the bulk, but on the coating, by creating a fluorination of the insulation surface, or nanostructured coating by, for instance, using inorganic coating containing nano silica, okay? And as you can see here, there is quite a huge reduction of space charge with both fluorination and also this nanostructured coating. What we did also is to apply a graphene-based coating by applying this coating by using a spray, a graphene spray, okay? As you can see here, this is without any coating, and you see a lot of accumulation, injection of negative charge. By applying a coating, this negative charge is significantly reduced at quite high field and temperature. And this is also evident looking at this plot where you see that without a coating, we see a huge increase of the space charge as the electric field increases. While if we have this coating that prevents space charge injections, you see that this is really reduced of several times. And also at high temperature, increasing the temperature, you can see that without coating, we have a big increase of the space charge accumulation, while with the coating, the space charge accumulation is very much smaller. So which are the requirements for good HVDC insulation? I've spoken a lot about space charge accumulation that should be reduced. The rule of thumb is the lower the accumulated charge, the better is the insulation performance. But also what we want to get is improving DC electric strength and voltage endurance, or having an electrical conductivity that is less dependent on temperature. And this is very important because it can reduce the electric field variation inside the material with the temperature, or improve the thermal conductivity for accessories and semicon material, having, for instance, a tunable conductivity. And all these things can be done by adding nanofillers to our electrical insulating material. There is also some additional requirements which came out very recently. The desire now is having not only better performing material, but also more environmentally friendly materials. This is due to the fact that cable manufacturers have to do the so-called life cycle assessment and eco-design of their equipment. So the use of XLPE, that is now the benchmark insulation that is used everywhere. The problem is that the XLPE is quite difficult to be recycled because it's a cross-linked thermosetting material. And also, the degassing process that is necessary to reduce the byproducts, to remove the cross-linking byproducts, is very energy consuming process. So the idea is to use not a thermosetting material, but a thermoplastic material. The polyethylene is not good because the melting temperature is about 110, 120 degrees, so not very good to work at high temperature, but the polypropylene is a very good candidate because the melting temperature is about 160 degrees, and is a very, very good dielectric material. The only problems is that the mechanical properties are quite poor. It's a very rigid material, and also the thermal conductivity is much lower than the XLPE. But now there are some polypropylene compounds using also elastomeric material or other material, not cross-linked, that are fully recyclable. They have a higher rating temperature, they can be used at higher voltages, and also they can have good mechanical properties and thermal conductivity. So the research frontier for this kind of material is also the addition of nanofillers to improve further the properties of these polypropylene-based compounds. So to conclude, because it's now time to finish my talk, as I told you, HVDC transmission systems will be the backbone of the future power grid, at least in Europe, but as I told you, also worldwide, we have, let's say, the use of HVDC system is growing. Most of these HVDC power lines will be made by insulated cables, and the voltages now are increasing and exceeding 600 kilovolts. So the insulation field, the design field should increase further. Now it was less than 10 kilovolts per millimeter some years ago, and now cable company want to exceed 30 kilovolts per millimeter. This further increase also will be in operating temperature. The cable company wants to exceed 90 degrees, go perhaps to 110. And of course, space charge could be a problem in that case. So we need new insulating materials, nanocomposite blends, to have reduced space charge accumulation, better endurance, and properties that are tailored on the application. Also, be very careful because we need also to be eco-friendly for the future. Okay, I finished.
Thank you, David.
Thank you so much, sir, for
You can continue.
Yeah, thank you so much, sir, for conveying us such effective information. It was indeed a privilege to learn from you, sir. Now, I am pleased to invite our branch counselor, Ms. Madhavi ma'am, to deliver a vote of thanks.
Thank you, Sindhu. Good afternoon, everyone. On behalf of IEEE VECSB and IEEE DEIS, I would like to extend my heartfelt gratitude to Professor David Febernine for sharing an expertise on HVDC cable installation, which has greatly enriched our understanding.
Thank you.
For
Sorry,
accepting.
I had some problem.
Thank you so much.
Could you hear me? Because I had some problem at the end of the presentation. I had some network problems, so I had to connect again to the web.
Yes, sir. Yeah.
Okay, very good.
Thank you, sir. A big thank to our organizing teams, Sneha Hegde, Venkat Sai, David Raju, Miss Sindhu, Amulya, and my volunteers for their hard work, to our engaged participants for your participation. Finally, thanks to our IEEE for fostering global collaboration and innovation. Let's continue this type of cooperation and collaboration for future.
Yeah,
thank
sure.
you, sir, for accepting.
Thank you.
And team also I want to thank and congratulations. Thank you, sir.
Thanks.
I had a quick question before we wrap up.
Sure,
It's a very it's a very general question, because we all are taking part in this huge conferences related to climate change and stuff, and of course we hear a lot about how they want to triple the renewable energy in the coming years. But again, the as you said, in EU and UK, they are planning to collaborate and do a lot of main projects. But what they are lacking currently, from what I've read from the company like Nexans, that the companies are booked out for the next 20-50 years regarding manufacturing. They don't have materials. They don't have skilled workers who can do this work, and also the materials that are required for this. So what do you think, Davide? How are we going to tackle, when you hear all these things? I mean, it's very nice to hear that in next 10 years we need 10,000s of gigawatts of energy, but how do you think is it feasible?
Sneha, this is really a huge problem. You touched, how can I say, that what is the main problem worldwide? I talked with some former student of mine. They are now working in Prysmian, and they told me the same. They are fully booked till 2032. And the problem is not only the facilities for building, for creating, for manufacturing new cables. It's also the facilities to test the cable, because each cable has to be commissioned, has to be tested after and this takes time. And they are building new laboratories, new big laboratories. They build other 3 laboratories in Italy to have facilities to test the cable that are manufactured. But the problem is that if the world will require a so huge renewable energy demand, then I don't think that we will be able with the current company to provide all the equipment that are necessary. So there will be perhaps space for new company. I think, for instance, in China or also in India, there could be new manufacturers that can work in this kind of field. I know for sure that there are some raw material providers that are now trying to invest in creating materials for HVDC. So in addition to the existing one. So I guess that it will take a little bit of time, but there will be space for our, let's say, industrial people to grow and to create a new company.
Yeah, just a quick follow-up with Davide. So I definitely agree that it's a great opportunity for the new manufacturers who want to come in this field, and they can set up, maybe the government or the people also can help them. But again, a quick question. For example, in Italy, how well is the government connected to the academics or the labs? Do they get connected with the research labs? Are they in touch with the research labs on what is happening? Do they talk to you regarding the requirements that you have? Or where are we lacking in terms of research to reach that goal that Italy has, or in general?
Okay, I can tell you that we had, with the funds coming from Europe, the so-called Next Generation EU, that came after the COVID pandemic. Our government provided a lot of funds for university to create sort of joint labs with industry. And in particular topics like renewables, not only, of course, but also, for instance, HVDC. So we are now working together with some Italian companies, but not only Italian, to create some joint facilities. And so the Italian government gave a sort of incentive for creating these joint facilities between university, so academia, and industry.
Oh, that's great. That's great. I think you have another question from in the chat box, Patrick.
Yes, sure.
You can unmute yourself, Patrick.
Yeah. Thank you for the presentation. So I have a question regarding the, let's say, dielectric strength during polarity reversals.
Yeah.
So since the dielectric strength of polymeric insulation materials decreases significantly at higher frequencies, like at AC or at higher frequencies, is this breakdown phenomena really related to the accumulation of space charge, or is it more related, let's say, according to the fact that we have higher frequency components in the polarity reversal?
It could be both, because sometimes there is not only a problem of polarity reversal, but there are also some other kind of they called non-standard overvoltages, no? Transient overvoltages.
You mean the SFTOV or
yes, SFTOV. There is also that kind of problem, and this is not a space charge problem. It's a problem, as you were mentioning, of high frequency components that can, of course, create an additional stress. So let's say the slow polarity reversal, the one that are typically can be managed, no, on an hour basis, can have the impact of homocharge. If you have some homocharge in the material, can create an additional stress once it becomes heterocharged. But for fast change in the polarity reversal, so for fast polarity reversal, in that case there is also an additional problem created by the high frequency components that can be inside. Yes, I totally agree with you. There is also that additional problem.
Okay, and may I have a following question? So let's say we always talk about homocharges, heterocharges, and there are some, let's say, in the material, and some are okay, let's say. But do you have a critical value, let's say, for this accumulation of space charges, or for a field enhancement factor? So in which region we can use cables? For example, a field enhancement factor of 2 will be bad, or I don't know. So I don't know the value. Or a value.
Is there a good value or not? What I can say that there is a study group, a technical working group of our technical committee of IEEE DEIS that is chaired by Giovanni Mazzanti, a colleague of mine at University of Bologna, And they are indeed trying to standardize these kind of values. Considering the field enhancement factor, so the variation of the local field with respect to the Laplacian field, let's say that some numbers that I have seen are tolerated are below 5%. So if there is a homocharge, not heterocharge, and the electric field is the change of the electric field, so the field enhancement factor is below 5%, this is something that is tolerated. But it's, let's say, not written on the stone, I would say. No, it's a sort of value that comes from the cable companies. Okay, and in particular, TSO are a little bit concerned about if this value is really safe or not. Okay, so it's not a value that is, as I told you, written in the stone, but it's something that can be taken into consideration when you want to analyze a new material and saying, oh, this material could be a good candidate or not for the HVDC insulation. I don't know if I answered your question, Patrick.
You mean 5% for the cable or
for the cable? This is a value that, if I remember well, is came for after laying tests, for commissioning tests.
But
when you do the cable, the pre-qualification of an HVDC cable, you do also space charge measurements. If I remember well, in the version of the SIGRE technical brochure and of the standards that was written, IEEE standard that was written in our technical committee, the value, if I remember well, is below 5%, if I remember well.
But I think this value is quite low, because if you think about the,
I know that it's quite low,
the fact that you have a field inversion, then you may get a better field distribution related to an AC cable, and then you save 5%. So in Graz, we are doing a lot of work with this medium voltage DC cables. I think you have heard already from that. And we have done some PA measurements, and there we started in a field enhancement factor, which was
10.
If I remember correctly, it was somewhere in the range of 2 or 3, and the cables passed the pre-qualification test and type test without any objections. So
okay, yes,
we have also tried. Yeah, we have also tried polarity reversals, and we don't see a breakdown of 5. Yeah, and that will be a range of 100 to 200% field enhancement factor, and not only 5%. So 5% is really low.
Yeah, this is for, remember, it's for extra high voltage cables. So cables above 525 kilovolt.
Okay,
where
so
the design field is very high. Okay.
Okay.
So for medium voltage HVDC cables, you can tolerate, I guess, much more, because the electric field, the design field will be lower, I guess, than for 525 kilovolt.
Okay. I have a last question, if there is time for that.
I'm completely full, free up to 12, so no problem.
That's perfect. That's perfect. The publications which we are able to find normally in IEEE about this polarity reversals and breakdown according to polarity reversals are mostly made before the year 2000, and the other insulation material was quite pure insulation material in the case of XLP, because we had a lot of improvements in terms of quality and quantity of the materials, the cleanness, and so on.
Yeah.
Do you know if there were some further investigations after the year 2000 about this breakdown related to polarity reversals, where you see this significant decrease, let's say?
Well, you see that, it's our investigation was done under a European project called HVDC, and so some of the measurements that I showed, in particular the one with the endurance tests, was made in the, let me say, between 2003 and 2006, okay? Then we didn't do addition. So we found that at that time, with some insulating material, not all insulating material, some insulating material, we found a significant reduction of reliability with polarity reversals associated with the space charge accumulation, because we did space charge accumulation and continuous space charge accumulation. The problem is that after that time, we didn't do so much test on polarity reversals. So as far as I know, there are some, let me say, I've seen some works relevant to space charge accumulation. The last one were made at TU Delft at the end of 2010, I guess. There is something made by Xi'an Xiaotong University, so works made by Professor Kai Wu. I don't remember exactly when, but they should be later than 2010, so it could be 2015 or like that, and nothing more after. So yeah, I agree with you that perhaps with the new materials, which are purer materials, perhaps also with the use of nano fillers, the effect of polarity reversal could be much less. So it could be less significant than in the past. So yeah, but
and it's not really possible to have a look if it's really related to space charges or to the frequency.
No, it's not impossible. Yeah,
or...
it's not impossible to see, because you can do both space charge measurements and endurance tests at the same time. So it's possible to see if there is, after polarity reversal, you have a huge transient in space charge activity, and then this leads to failure. It's possible to see it.
Okay.
Yeah.
Perfect. Thank you very much.
Thank you, Patrick.
Thank you.
Yeah, thank you all. I would like to ask all the participants to turn on the cam for a bit.
Okay.
Sneha, Gaurav. Also the participant from BC.
Sorry, wait.
Okay, so
wait, give me 1 second. Only
no problem.
Geht das mit der Kamera nach? Ich glaube, meine Kamera geht.
Okay, I think we are good to go. There we are. Okay, then. But again, like to thank Mr. Davide for accepting our invite.
Thank you everyone. Really, I enjoyed staying with you for this time, and I hope to see you again very soon. No? Perhaps at some events organized in person by the DEIS, conferences, webinars, workshops, summer school. Why not? If we are able to organize the summer school in India, this year could be very interesting. I think it's a great opportunity for the student chapters that we have. We are growing a lot in India, and then we are very, very happy to do it. So
one question about which topic will be the summer school?
I have to ask with Professor. So she will be organized by Nandini Gupta. So I can ask. Typically, the summer school are related some way to HVDC. The last one that we had were related to HVDC applications. So, but to be honest, I have to ask, because we will next year we will organize 2 summer schools, one in India and one in China. So I have to ask which are the topics. But if you are interested, of course, you can reach out to me, let's say at the beginning of next year, and I can send you more information. If you are DIS members, student members, or regular members, you will receive the email, because we are advertising the summer school by using e-notice.
Okay, good.
So
Yeah.
Davide, sorry,
Sure.
go ahead.
No, I was on one summer school that was really good. So in Monmouth with Peter and with John.
Yes,
and
yes,
so
yeah.
Okay, so
Yeah, Peter will
Thank
be
you.
involved in the summer school in China for sure.
Yeah.
Peter Morshaus. Not sure who will be. Let's say I guess that also in India there will be an involvement of the traditional summer school organizer, which are Peter Morshaus, Thomas Andrich, John Fothergill, and these guys, let's say. So they will be involved also in the 2 summer schools next year.
thank you.
You're welcome, Patrick.
So
Snea,
do you know during which period we will have this?
I'm not sure 100%. It could be during the summer, because it's a summer school. Of course, I think that in India will be very hard to have something in the summer. Perhaps it will be
Actually,
inside with air conditioning, I guess. Yeah, typically these summer school are held in August. But you are right. I will write to Nandini Gupta to ask her some more details, because of course it's important to have at least a first brochure, first brochure to be sent to DIS members, and also to potential DIS members or interested people. Even if they are not DIS members, they can join, of course, the summer school.
And I think for the members who don't read their emails or e-notices too much, we can send. We can also do the promotion through our YP and WIE LinkedIn pages, or the social media pages.
Using LinkedIn, and whatever. Yes.
Yeah.
Also, we can try to reach out to supervisors, because supervisors, they have students. And of course, it's perhaps easier to try to contact the supervisors in India or in other countries. Yeah.
Yeah, that sounds good. Yeah. Okay. Yeah. Thanks, Davide.
You're welcome.
A big thanks to our speaker, Professor Davide Fabiani, sir, and thank you all the participants for joining us today. Have a great day ahead. Thank you.
Thank you. Thank you, everyone. Have a good evening.
Thank you.
Bye-bye.
Have a nice day. Bye.
Bye-bye.